Hello everyone, this is Saber, the Smart Circuit Breaker team. My name is Eli, an electrical engineer, and
I'm Carter, I'm a computer engineer.
I'm David, I'm a computer engineer.
I'm Emmanuel, and I'm an electrical engineer.
So, what is the Sabre Smart Breaker? The Sabre Smart Breaker looks to innovate on the conventional residential circuit breaker by incorporating solid-state tripping mechanisms, current and thermal monitoring, Internet of Things connectivity, and an intuitive user interface all into a compact, self-contained unit. This innovative design allows for easy replacement with standard name brand circuit breaker boxes, something that current market offerings fail to do.
Existing products in the market often feature non-standard designs and necessitate the installation of proprietary breaker boxes alongside individual breakers, significantly increasing the cost of upgrading to smart grid technology.
The design features 4 distinct custom PCB boards, each dedicated to specific components based on their functionality. The first PCB shown is the regulator PCB, which is responsible for rectifying and regulating the main signal down to a 5-volt DC signal, which is in use for distributing power to all of the embedded components. The regulator is powered from the main signal line, which is fed through the wire screw terminal seen here. The signal is then rectified through the full bridge rectifier, which is seen here, composed of 4 high voltage Schottky diodes. This rectified voltage becomes equal to roughly 40 volts DC. The signal needs to be smoothed out before actually feeding the regulator IC, so due to that, a 4700 microfarad capacitor is placed in parallel to virtually remove the voltage ripple introduced through rectification. After which, the smoothed out DC signal can actually be fed into the regulator. The smaller capacitors on the input and output of the regulator are used as a bypass and a help in regulation respectively, while the large inductor seen here is used for providing the appropriate feedback for the regulator to switch on at the desired frequency to produce the 5-volt output. In addition, a Schottky diode is used in reverse bias on the output as an additional clamping mechanism.
This second PCB is the sensor PCB, which is responsible for carrying the main signal line to the load while also passing through the sensors and relay for actually tripping the line. The main signal passes through the wire screw terminal seen here before passing through the solid-state relay, which is responsible for actually tripping in accordance to user input or exceeding thresholds. The signal then passes through the Hall effect sensor, which produces an analog voltage equivalent to the current passing through it, which allows the MCU to have an accurate measurement of the current being supplied to the load. Finally, the temperature sensor is placed directly on top of the main signal trace to monitor the temperature of the PCB and to report to the MCU to trip the signal if temperature thresholds exceed a set threshold. The main signal is then routed back to the other side of the wire screw terminal, where it can be directed to the front-facing screw terminal actually connected to the load.
This PCB is the main driver for the LCD display located on the front of the breaker. It utilizes the FBI protocol to communicate with the ST7889 TFT driver embedded with the LCD display itself. As can be seen, this is a linear regulator on board to drop the 5-volt signal down to the appropriate logic level of 3.3 volts for use with the display. In addition, the backlight is powered through a 60 mA constant current driver, which as the name implies, outputs a constant 60 mA to the backlight so long as the 3.3 volt regulator supplies it. All of the respective signals here are connected to the 30-pin ribbon connector, which is what the LCD itself slots into to be able to take the communication signal present on the driver PCB.
finally, we have the MCU board, which is responsible for housing the MCU and providing header for the other PCBs mentioned previously to provide their respective input and output to the ESP32, which is situated at the center of the board. The right side of the board is mostly made up of the respective circuitry for programming and serial communication over USB, which is done with the CP2102. A 5-volt header is located on the right side, which is where power from the regulator is distributed to this PCB itself. And then from there the LCD driver PCB and sensors PCB, This 5-volt signal is passed through a linear regulator on board the PCB to provide the appropriate 3.3 volts logic levels for the ESP32. An 9-pin header is located at the bottom to deliver the necessary signals to the LCD for performing SPI communication. The 3-pin header on the right is used for the trip button and for the reset button located on the outside of the chassis. The 5-pin header in the top left is what is used to communicate with the sensor PCB, gathering the analog voltage signals provided by the two sensors and to provide the signal from the MCU to the SSR for performing the tripping mechanism.
The chassis that houses all these PCB components is modeled off of the Square D 2-pole circuit breaker and is 3D printed with PEDG filament. The clips on the back are what slots into the actual breaker itself, providing conductivity between our simulation grid and the breaker itself. And the front screws are the input terminals for wires that go out to the load itself. The small button on top is just a reset button, while the button on the front is for manually tripping the breaker locally. So this is what a setup and provisioning stage would look like. As you can see, it's going to ask me if I want to enter new thresholds. For in this case, I'm going to enter in some new thresholds. I entered in 20 amps and that far exceeds the threshold of 5 amps, so it's going to tell me that's invalid and ask me to input it again. This time I'm going to do 4 amps and it will accept it. It's going to ask if I want to enter Wi-Fi credentials. I will put in some new ones, so we'll do something just random here. So generic, Wi-Fi credentials. Ask for a password. I'm just going to click randomly. And it's going to attempt to connect. And after 10 attempts of trying to connect, it's going to fail because that's not what my network connectivity is. So this time we'll actually input the correct things. And now with proper Wi-Fi credentials entered, it's going to connect, and then it's going to connect to the dashboard. As you can see, the 2 icons in the top right have gotten the X removed. So now I'll try to connect to an account. So this is an account that doesn't exist. So john@gmail.com, account not found. It's going to ask me to input new credentials. This time I will use proper credentials for an account that already exists. Enter the password associated with said account. X will disappear, and we are ready to start. And now here's just an example with saved credentials. So just to make it so that every time the breaker resets or turns back on, you don't have to re-enter all of these. They will be saved in non-volatile storage. And as you can see, after 5 seconds, it's just going to use the default that was already saved previously, in which case it should already connect accordingly, because if it was already connected before, it's just going to reconnect using those same things. So it's going to use the saved account credentials now. And once again, we are ready to start. Alright, and I can come on the web app here, and I'm just going to sign in using the same account credentials that I used for the device itself. And as we can see, the device is currently online and monitoring on the said account. I can go to the logs page and I can look at some of the past saved values that were logged to the remote dashboard. As you can see, here are the logs for today. You can see the red areas showcase the inactive tripped regions, green line showcases the current, while the orange line showcases the temperature. Alright, so we're going to do the demonstration of our engineering specs. So as can be seen here is the transformer which simulates our main power grid. It's just going to connect to the back of the breaker itself, which goes into the screw terminals, which the breaker clips directly into to get proper conductivity. Here we have what we're using for the resistive load, so it's 2 high wattage potentiometers, specifically 0 to 100 ohms and 0 to 500 ohms, which allows us to manually adjust the current that will be supplied to the load upwards from about 300 milliamps all the way up to over 5 amps. Alright, so we're just going to showcase the voltage at the terminals. So at the back terminals where the simulation grid directly connects to it, as you can see, about 30 volts AC. We'll go again and measure it. As you can see, it's still about 30 volts AC, a little under 29, 28 terminals. So now we'll move over to the front terminals, which actually connect to the load. And while it's active, as you can see, getting about 29 volts once again, AC. Take it off, do it one more time. And once more. Alright, so now we're going to showcase the max operating current. So I have the threshold set to 5 amps, so once 5 amps is exceeded, the breaker will automatically trip, and we're going to cover the entire scope all the way from 1.7 amps to 5 amps by just turning the potentiometers, lowering the resistance, thus increasing the supply current going to these loads. As we can see, keep spinning them. Current is increasing, it's increasing. And once we've exceeded 5 amps, the breaker will automatically trip. We can see that with the multimeter for comparison that there is currently no current flowing through. I can try to manually retoggle it, but since it's still at 5 amps, it's going to instantly toggle right back off. We can do this again, and same outcome, it toggles right back off. And no current is allowed to pass through. Alright, and here's just a showcase of continuous supply current to the load. So it's right underneath 5 amps, so it doesn't automatically trip itself. And I can just come over here and manually trip it on and off. And as you see, every time that the button's toggled, the breaker will flip and no current will be allowed to pass. But then I can toggle it back on, and as we can see, back up to around 4.9 amps passing through. Alright, and so it's currently inactive, but I can come over here on my dashboard, manually trip it, and we're back online. And as you can see, we're reading about 4.9 amps once again. And for the final test, we have the remote latency test. So on screen, we have the LCD display. We have the multimeter as just a basis of comparison. Remote dashboard right in the middle, and then just a timer to showcase the speed of the tripping. So I will go ahead and now trip the breaker remotely. And as you can see, in under a second, it goes from 4.5 amps down to 0. We'll go ahead and do it again here. This time about 700 milliseconds. And once again, about 716 milliseconds for the last attempt.